Hello and welcome to our group presentation on Pythagorean triples. In this video, we will be going over the foundations of Pythagorean triples, the history that goes into it, the real life world applications, and we will also be proving Pythagorean triples and showing the lemmas that go into it. Okay, so what is a Pythagorean triple? Oh my gosh. A Pythagorean theorem is one of the most recognized results in mathematics, and it links algebra to physical space. The Pythagorean theorem, which states that for a right triangle with legs A and B and a hypotenuse of C, the relationship a squared plus b squared equals c squared holds. This is arguably one of the most recognized and fundamental results in all of math. It forms this building block of Euclidean geometry and provides a direct and interesting link between algebra and the physical space we perceive. Our group, we chose to focus on the study of Pythagorean triples because they represent a perfect and fascinating intersection of this geometric principle with the intricate world of number theory. So, the core question that drives this topic is honestly really simple. When do all three sides of a right triangle have integer lengths? A set of three such positive integers a, b, c is known as a Pythagorean triple. Going into the history, the search for these triples is not something that was discovered in the 21st or 20th century. This dates back thousands of years and is a subject rich in history. Clay tablets, such as the famous Plimpton 322, reveals that Babylonian mathematicians were studying and writing these triples for over 1,000 years before Pythagoras, for whom this theorem is named after. The long-standing human fascination with the hidden number order behind basic geometric patterns is demonstrated by this age-old effort. So, what me and our group, what we found really interesting about this problem, which begins essentially in geometry, it quickly transforms into a pure problem of number theory. We're no longer drawing triangles, but rather seeking integer solutions to an algebraic equation, which are known as Diophantine equations. The term comes from the 3rd century Greek mathematician Diophantus of Alexandria, who was famous for investigating such equations. The equation a squared plus b squared equals c squared becomes a gateway, the methods used to find and classify these triples, methods like factoring, modular arithmetic, and greatest common divisors, reveal deep structural properties of the integers themselves. We move from measuring objects to studying the architecture of whole numbers. So, primitive triples. Our exploration will focus on mainly on these primitive solutions, those where the sides A, B, and C share no common factor greater than 1. They are base units from which all other triples are derived. For example, as you see, 3, 4, 5 is a primitive triple, and its multiple 6, 8, 10 is not. By understanding how the primitive triples are generated, we gain the complete map of all possible Pythagorean triples. The primitive ones are the building blocks. So, in the coming segments, our group will take you through a detailed exploration of this topic. We will focus on the structure and generation of Pythagorean triples, proving the central theorems that characterize exactly how to generate all primitive solutions. Finally, we will discuss their lesser known yet highly important applications in modern math, cryptography, and real world systems. We hope you enjoy this journey from the geometry of ancient Babylon to the pure number theory that continues to challenge mathematicians today. Thank you.
Hello, everyone. In this section, I'll be covering the key definitions we use when studying Pythagorean triples. These definitions will be the foundation for the lemmas and proofs that follow in the later parts of our video. A Pythagorean triple is a set of three positive integers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared. These sets arise from right triangles where c represents a hypotenuse. A more specific type is called a Pythagorean triple. A triple is primitive if the greatest common divisor of A, B, and C is 1, meaning that the three numbers share no common factor greater than 1. For example, the triple 345 is primitive because the greatest common divisor of 345 is 1. However, 6, 8, 10 is not primitive because it is simply 2 times the triple 345. This example helps show the difference between primitive triples and those that come from scaling. Understanding these two definitions is important because they allow us to classify Pythagorean triples and understand how they are generated. To explore the full structure of these triples, we next look at two main lemmas along with Euclid's formula, which systematically produces every primitive Pythagorean triple.
In this part, I will explain the important lemma that connects every Pythagorean triple to a primitive one, and this gives us a complete understanding of how all integer right angles are generated. Pythagorean triple usually have two types. Primitive triple have no common factor, but non-primitive triple have. To understand all the triples, we want to see how every non-primitive triple relates to a primitive one. And this is our lemma 1. Every Pythagorean triple ABC can be written as ABC equal to KD, KE, KF, and K is natural number, and where DEF is primitive triple. And this is our proof. Given the Pythagorean triple ABC and we let G equal to greatest common divisor, and we divide each term by G, then we get a smaller primitive triple DEF. And the greatest of the DEF, greatest common divisor of DEF is 1, so DEF is the primitive triple. And here's our example. And given the triple 9, 12, 15, and the greatest common divisor is 3. And now we divide the 3, then we get 3, 4, 5. And the greatest common divisor of 3, 4, 5 is 1. So it is a primitive triple. And every non-primitive triple can be reduced by its greatest common divisor. And so the primitive triple are fundamental building blocks for all Pythagorean triples.
Hello, everyone. My name is Angel Poblano, and I'm here to talk about generating primitive Pythagorean triples. We will be doing this by using Euclid's formula and a key lemma in order to help us. So the overview is that I want us to recall that a primitive Pythagorean triple is a triple A, B, and C such that the GCD of A, B, and C equals 1, which means the three numbers do not share a common factor greater than 1. So our goal is to generate all primitive triples, and we will use a lemma forming perfect squares and apply that to help us prove Euclid's formula. So the lemma statement. The lemma states if x times y equals z squared, where x, y, and z are positive integers, and the GCD of x and y equals 1, then x and y are perfect squares. The definition is relatively prime, which means that two integers are relatively prime if their greatest common divisor, GCD, is 1. In this case, x and y are relatively prime numbers because their GCD equals 1. So to prove the lemma, we have to write x and y in terms of prime factorization because since the GCD of x and y equals 1, this means that x and y are relatively prime. Therefore, we have x equals p1 to the e1 times pm to the em, and y equals q1 to the f1 times qn to the fn. So prime factorization is a process of writing all numbers as a product of primes. For example, let's take 10. 10 equals to 2 times 5, which both numbers in those examples are prime numbers. So we want to recall that x times y is z squared. Therefore, that tells us that x times y is the product of two prime factorizations equals z squared. And we can tell because the GCD of x and y is 1, no PM will equal to Qn. So therefore, the product of x and y is a perfect square, which means that the product of all exponents must be even, which can be written as EM equals 2E prime M and Fn equals 2F prime N. Thus, both x and y must be perfect squares. So x equals P1 to the E1 prime times PM to the E prime M squared, and y equals Q1 to the F prime 1 times Qn times F prime N squared. Euclid proved that every primitive Pythagorean triple can be expressed with a or b being even or odd, and using two integers, m and n, such that a equals m squared minus n squared, b equals 2mn, and c equals m squared plus n squared, where m and n are positive integers, m is greater than n, and n is greater than 0, and the GCD of m and n equals 1, and m is not congruent to n mod 2. A primitive triple will always form if the conditions are met. So why one of A or B must be even or odd? So let's consider two cases. Case 1, let's suppose A and B were odd. So if A and B were odd, we have A equals 2m plus 1 and B equals 2n plus 1 for some integers m and n. If we square both of these, we are given these equations: 4m times n plus 1 and 4n times n plus 1 plus 1. A squared and b squared can be rewritten as a squared is congruent to 1 mod 4 and b squared is congruent to 1 mod 4 as well. And using Pythagorean theorem, we know that a squared plus b squared equals c squared. Therefore, c squared is congruent to 2 mod 4. Therefore, we are saying there exists a value of c such that c squared is congruent to 2 mod 4. In order to check this, we do 4 cases. So here we have if c is congruent to 0 mod 4, then c squared is congruent to 0 mod 4. If c is congruent to 1 mod 4, then we have c squared is congruent to 1 mod 4. If we have c is congruent to 2 mod 4, then we have c squared is congruent to 0 mod 4. If we have c is congruent to 3 mod 4, then we have c squared is congruent to 1 mod 4. So after checking all possible cases, we realize that there does not exist a value c such that c squared is congruent to 2 mod 4. Therefore, a and b cannot both be odd. So let's suppose case 2. Suppose a and b were both even. So if a and b were both even, then a, b, and c would not be primitive because a, b, and c will have a common divisor of 2. Therefore, a or b has to be even and the other is odd. Without loss of generality, let b be even. Therefore, adding will lead to c becoming odd because we have an odd plus an even, which will give us an odd number. Therefore, A and C are odd and B is even. So let's rewrite the Pythagorean theorem. As we know, it's a squared plus b squared equals c squared. So let's change that into b squared equals c squared minus a squared. So we can factor this right-hand side, and this will become c minus a times c plus a. We established that a and c are both odd numbers. Therefore, c minus a and c plus a will give us an even number. Therefore, we want to divide this by 2 because this will help us with the lemma. Therefore, our new equation is b over 2 squared equals c plus a over 2 times c minus a over 2. As I mentioned that we wanted to have this in order to help us add the lemma. So now we can introduce the lemma. We'll have x equals c plus a over 2, y equals c minus a over 2, and z equals b over 2. So we concluded that x and y are perfect squares, and the GCD of x and y equals 1 in the lemma. Thus, c plus a over 2 equals m squared, and c minus a over 2 equals n squared. So now we want to solve for a, b, and c. When we add these equations, c plus a plus c minus a, we can see that it will become 2c over 2, which is c. And we now know what these values equal to, and now we have c equals m squared plus n squared. When we subtract these equations, we can see that this would have been 2a over 2, which is why this equals a. And since we know their value as well, now we have a equals m squared minus n squared. And we want to consider x times y equals z squared because that was our condition for the lemma. So now we have b over 2 squared equals xy, which we know xy is m squared times n squared, which shows us that b squared equals 4m squared times n squared. And when we take the square root of both sides, we are now given that b equals 2 times m times n. We want to establish conditions on m and m, and it's important we follow the conditions because our goal is to generate primitive Pythagorean triples. So if the GCD of m and n does not equal 1, then a, b, and c shares a common divisor, which leads to the triple not becoming a primitive. And if m, and n had the same parity, then the formula m squared minus n squared, 2mn, and m squared plus n squared will be even and therefore not a primitive. Therefore, the requirement for m and n is that they are relatively prime and of opposite parity in order to generate primitive triples. So here are some examples I have made in Desmos in order to show us. So here is our base case for any Pythagorean primitive triple. We have m equals 2 and n equals 1. We know that these are opposite as this is even, this is odd, and m is greater than n. And we see how this works. We get 3, 4, and 5. If we make this odd and this even, we can then see how this also works as well. 5, 12, and 13. But here are some non-examples. If we let m be less than n, we see that we get a negative number here, which already tells us that this doesn't even follow the formula of the Pythagorean theorem. Therefore, we know that this can't happen. Therefore, we know that m must be greater than n. And we know m and n cannot be the same because if we had m and n both be even, we see here that this is no longer a primitive triple, as we can see that this all have a common divisor of 4. So that's why it's important that we must follow the rules and the conditions for m and n. So to summarize, every primitive Pythagorean triple comes from the formula a equals m squared minus n squared, b equals 2mn, and c equals m squared plus n squared, with m greater than n greater than 0, the GCD of m and n equals 1, and m and n are opposite parity. This equation gives us all primitive Pythagorean triples. Therefore, we have proven Euclid's formula on how to generate all primitive triples. Thank you.
In this section, I will talk about how Pythagorean triples appear not just in math, but across history and modern technology. They show up anywhere we need right angles, distances, and spatial measurements. So the Pythagorean are used in many fields like architecture, engineering, physics, and computer graphics. And the early builders discovered the rope tied into 12 equal segments could form 3, 4, 5 triangle, which guaranteed a 90-degree angle. And they made it an essential tool for laying foundations and building street walls. Yeah, look at this picture. It's a 12-segment rope and form a 3, 4, 5 triangle for 90-degree corners. And sometimes they also use the 5, 12, 13, and 12, 21, 29 to find the slope and right angles while doing the pyramid construction in Egypt. Look at this pyramid construction. They usually use the Pythagorean theorem to find the right angle and the slope. And the idea behind the Pythagorean theorem also extends beyond two dimensions. In 3D geometry, we use the same concept to calculate distance between 2 points in 3D dimension. And the formula, look at this. This is the Euclidean distance. The formula is d equal to square root 2 squared plus b squared plus c squared. And then we can find some graphs like this. This is the 3D graphs. It's a surface of the paraboloid. And the function of this graph is fxy equal to x squared plus y squared, which is related to distance calculation in xy plane. And in the modern computer graphics, this is very heavily depend on the Pythagorean Pythagorean type calculation. When 3D object is rendered on the screen, algorithm use vector, length, projection, and transformation, all based on Pythagorean relations. And this picture shows the 3D transformation from one position to another position, more likely the matrix transformation. And in math, we also use the Pythagorean theorem to find the angles and such as the sine, cosine, and this equation of the unit circle and the fundamental identity involves sine, cosine, both come directly from the Pythagorean idea of distance. And the Pythagorean also can be used in the physics and the navigation, such as the radar system, GPS, and by finding the distance between the objects. This picture shows the synthetic aperture reader. It uses the Pythagorean theorem to calculate the slant range and the high resolution and create high resolution images.
All right, in this final part, I want to highlight why Pythagorean triples remain an important topic in both geometry and number theory. These triples show how simple integer relationships can form the structure of right triangles. Using Euclid's formula, we can generate every primitive triple, revealing patterns that continue to appear in modern mathematics and engineering, as well as computer science. The connection between numbers and geometric shapes makes Pythagorean triples both elegant and timeless.